Okay, so welcome back everyone. So in today's video, we'll take up uh, we'll take up two problems from SBT. Okay, so the first question is from the chapter Work, Power and Energy. Okay, and this is question number 92. So we have a tube whose mass is capital M, and it hangs from a thread, and two balls of mass small m slide inside it without friction. So the balls are released simultaneously from the top of the ring and slide down on opposite sides. Theta defines the positions of the ball at any time, as shown in the figure. Okay. So question A is like we have to show the ring starts to rise if the small m is greater than or equal to 3m by 2, and if the mass of the ring is small. If the mass of the ring is negligible, find the angle theta at which the tube begins to rise. Okay. So yeah, give this problem a try, guys, and check out the solution. Okay. Okay, so this is the diagram of the given situation. So initially these balls, when they start from this location, they start with negligible speeds. So then they start accelerating and start picking up speed, right? So when they just begin, the normal reaction on the red balls will be radially outwards, right? So like for example, let's say when they are at this particular location, it doesn't have much speed, right? So the component of mg, let's call it mg parallel, in order to balance this, the normal reaction will be radially outwards. So initially the normal reaction is radially outwards, but after a while what happens is the ball starts picking up speed, and then what happens is the ball will go and hit the outer surface of the ring, and the normal reaction will become inward. Okay, so we'll write down a function and try to figure out when that happens. So firstly we can just conserve energy and find out the velocity at this particular instant. So v squared is just going to be u squared plus 2gh. So the height by which it dropped is going to be r minus r cosine theta, right? So this is going to be r 1 minus cos theta. So we have the velocity at this particular instant. So at this particular time, let's say the normal reaction is radially outward, and the component of mg, in the radial direction is mg cos theta, right? So we can say the inward force, that is mg cos theta minus a normal reaction, equals mass times the acceleration, and acceleration will be centripetal v square by r. Okay, so now let's substitute the value of v square in here. So we get the normal reaction as mg times 3 cos theta minus 2. Okay, so if you put theta equal to 0, you'll get n equals mg, which represents the top position. But here if you observe, n is a positive function till cos theta equals 2 by 3. After that, it is a negative function. So normal becoming negative just means that it becomes inwards. It becomes radially inward. So okay, so basically from theta lying from 0 to cos inverse of 2 by 3. So it which represents the starting position till the position when normal reaction becomes 0. The normal reaction is actually radially outward, and after this point what happens is the normal reaction becomes radially inward. Okay, now we are more interested in the radially inward part, and okay, so let's call the angle cos inverse of 2 by 3 as theta 1 for some time. Okay, and let's say the ball has covered the angle of theta 1. So what that means is that currently the normal reaction between the ball and this tube is actually 0, right? So and after this point the normal reaction will become radially inward. Okay, now as the normal reaction on the ball is radially inward, by Newton's third law we can say that the same normal n will be acting on the tube in the radially outward direction. So on the tube it is going to be something acting in this particular direction. Okay, and so let's say this angle is some theta, which would mean even this angle is theta, and it's the n cos theta. So basically the normal reaction that is trying to lift up the tube is 2n cos theta, right? So this is the normal reaction that is trying to lift up the ring. Now, okay, so from looking at these two diagrams, it will be clear that we want the normal reaction on the ball to be radially inward, because only in this situation is the normal reaction trying to lift up this ring. Okay, which means we are more interested in the theta which is greater than theta 1. Okay, in this situation when theta is greater than theta 1, we know the normal reaction is just the negative of what we found out. So it'll be mg times 2 minus 3 cos theta. Okay. So now Ny, which is the lifting force on the ring, is going to be 2 n cos theta. So which is 2 mg times 2 cos theta minus 3 cos squared theta. So now it's okay. So now this is the function Ny as a function of time. Now in the first question, we want to figure out what is a minimum m such that it starts to rise up. So the minimum value of small m will obviously be the case in which the ring is barely lifted up, right? So let's try to figure out the maxima of Ny. So for that, we can just find dNy by d theta and set it equal to 0. So this will be minus 2 sine theta minus 6 cos theta sine theta, and we set it equal to 0. So from here we get cos theta equals 1 by 3. So this corresponds to our value of theta at which Ny is maximum. So when Ny attains its maximum value, we want the ring to be just lifted, right? Okay, so the idea is that when Ny attains its maximum value, we want the ring to be just lifted up. This will give us the limiting value of m for which it rises up. Okay, so Ny, so the maximum value of Ny, we'll just put cos theta equals 1 by 3 in the expression. So we'll get 2 mg times 2 by 3 minus 3 by 9. So this just becomes 2 mg by 3. Okay, so the maximum lifting force on the ring, which is 2 mg by 3, if this is greater than or equal to the weight of the ring, then it will be barely lifted up. So this just gives us the condition that small m must be greater than or equal to 3m by 2. Okay, so this was the required answer. So this is what we had to show for the first question. The second question, they're asking if capital M is 0, then find the angle theta at which the tube begins to rise. Now, so basically they're asking if the ring is massless, then when does it begin to lift up? So the answer to this is pretty simple, right? As it is massless, we only need a negligible amount of force in the y direction to actually lift it up. What that means is we want the normal to switch. We want the normal reaction to reverse its direction. So basically it will be lifted up when theta equals theta 1, which is basically cos inverse of 2 by 3. So this is the instant when the ring will be lifted up if it is a massless ring. Okay. So yeah, that was it for this question. Now let's move on to the next one. Okay, so this is the next question. So we have a uniform rope whose length is pi r by 2. So it occupies 90 degrees of, so it occupies a quarter circle basically. It has been placed on a fixed cylinder of radius r as shown in the figure. One end of the rope is at the top of the cylinder, and the coefficient of friction between the rope and the cylinder is just enough to prevent the rope from sliding. Mass of the rope is given to be capital M. At what point the tension in the rope is maximum? Okay, so we need to figure out when does tension achieve its maximum value along the rope, and also we have to calculate the maximum tension. Okay, so let's begin with the analysis. So now before beginning with this question, guys, let's discuss a very like a small result. Okay, so let's say we have some arbitrary curved trajectory. Okay, and let's say we keep a chain or some kind of a rope along the trajectory, and then we release it. Okay, now obviously the curve actually continues. All right, it doesn't stop here. Now if we release the rope, what will happen is it will start sliding down, right? Okay, and it is going to have some acceleration a. Now the way we find out this acceleration is by looking at the force that is trying to move it along the slope. For example, let's say we take a small element, something like this, and let's say its mass is dm. Okay, so now let's zoom in the element to emphasize the slope, and let's just say the slope on which dm is kept makes an angle theta with the horizontal. Okay, now here there will be the force of gravity on dm is dmg downwards. Now the force that is trying to move it along the slope is actually dmg sine theta, right? So in short, if we choose any small dm mass at any location, the force that is trying to move it along the slope is actually dmg sine theta. right? So if you integrate dmg sine thetas from beginning to end, we'll get the total force that is trying to move the rope along the incline. So its acceleration is nothing but integral of dmg sine thetas divided by the total mass, right? Okay, so here what we can do is, now the dm in the numerator, I can write it as lambda times the length of that element. So if I say this element has a length of dl, the dm I can write it as lambda times of dl and multiply it with sine theta. Now this thing over here, dl sine theta, from a differential triangle, if you observe, dl sine theta is the height of this triangle. So if I call this height as dh, this is nothing but g lambda times integral of dh. So basically, if you add up all the dh elements from beginning point to the end point, what you end up is the height difference between 1 and 2, right? So let's call it as h12. So the integral dh just becomes h12 divided by m. Okay, so basically in one line, the final result is that the force, that is the force of gravity that is trying to move it along the incline, right, is actually lambda gh, where h is the height difference between 1 and 2. Okay, so this is the result that we're talking about. Now there is also a very interesting result for friction, provided it is limiting in nature. In the same triangle where we had the dm mass, the normal reaction, let's call it dn, on this dm mass is going to be dmg cos theta, right? So if you want to write, the friction force df, assuming it is limiting in nature in this situation, I can write it as mu times the normal reaction, right? So now the normal reaction is dmg cos theta, and similarly if you integrate dm, you can write it as lambda times dl, and here if you observe, the integral becomes integration of dl cos theta. So the integration of dl cos theta, similar to what we did earlier, is going to be the horizontal difference between point 1 and 2. So this is going to be lambda mu g, I'm going to call it as delta x. Okay, so this is the total friction force acting on the rope. Okay, so these two results are actually pretty useful. It'll make the calculations a little bit easier. Okay, so the first thing we need to note here is that the mu, or the friction coefficient, is barely sufficient to prevent sliding. Okay, which means it's literally on the verge of slipping. So what will happen if the rope started slipping downwards? So the friction on each of these elements will become limiting in that situation, right? So that's what is happening right now. So if you take a very small element, the friction on that is going to be the limiting friction. So the first idea here is that, so let's separate out the rope and write it sideways. So the friction force, I'm marking it with purple arrows. Okay, and the thing is, using our previous result, we can just directly write this. So the friction force is equal to mu multiplied by lambda g delta x. So this would be mu lambda g, and the x difference between this start point and the end point is equal to the radius, right, which is just capital R. Okay, so this is the total friction acting on the rope. So now let's talk about the gravity, the force of gravity that is trying to move the rope along the slope. So that is also a one-liner. So the force of gravity that is trying to move is going to be lambda g delta h, which will be also R in this case, right? Now the thing is, there is no other force, right? The normal reaction is perpendicular to the rope at each and every point. So that is not trying to move it along the slope, right? And tension forces are just internal, and internal forces have no role to play in the acceleration if we consider the net force, right? So here the force of gravity that is trying to move it should be balanced by the force of friction, right? So from here what we get is the coefficient of friction is equal to 1. Okay, so now we finally determined the coefficient of friction. So now let's take a random element at some angle theta and between a differential angle of d theta. So we are talking about this element over here. Okay, so this is the element that we're talking about. Once again, guys, the gravity force along the slope is dmg sine theta, right? So I'm just drawing it like this. So along the tangent, the gravity force is dmg sine theta, and the friction force is going to be dmg cos theta, and then there will be some tension T and T plus dt, right? So because it might just vary from point to point. So I am just writing it as t plus dt. Okay. Now in the question, if you observe, what they asked was the maximum tension. Now tension is obviously a continuous function from 0 to 90 degree, right? So if it has a maxima, what that means is dt by dx is 0, or basically around the maxima, the tension does not change much, or basically dt is equal to 0. So if I set dt equal to 0 to find out the condition for maxima, then from the FBD, t cancels out with t, and we get, so I missed a mu here. We get mu dmg cos theta equals dmg sine theta, right? So from here, tan theta turns out to be mu, but mu we figured out it was 1. So theta turns out to be 45 degrees. Okay, so theta equals 45 is the point where tension achieves its maximum value. Okay, so that was the answer to this question. So now now we have to figure out the tension at this point. Okay, so obviously what we'll do is we'll cut the rope at theta equals 45. So let's actually just go ahead and do that. So we'll borrow this old diagram. Okay, and we're going to cut it along the 45 degree line. So, and let's get rid of the upper half and draw the FBD of the lower half. Okay. The original goal was to find out the tension at this location. Okay. So this is also the maximum tension, and this angle was 45 degree. So once again, we can use the same trick that we used till now. The force of gravity that is trying to move it along the slope is proportional to this height, right? And this height is actually equal to r sine 45, which is r by root 2. So basically T max, we can write it as Fg minus the force of friction, right? So Fg is going to be lambda g r by root 2. And the force of friction is mu lambda g times delta x. So the x difference between these 2 points is capital R minus r by root 2, right? So this is going to be r times 1 minus 1 by root 2. So if you take lambda g r common, so this would become square root of 2 minus 1. Okay, so now we can express lambda in terms of the mass of the rope. So the mass divided by the length of the rope, which was pi r by 2, is lambda. So the maximum tension just comes out to be this particular value. Okay, so we figured out T max as well. So that was for this question. So now let's talk about this question 121. Okay, so we basically take the same rope and we place it on top of the cylinder like this. Now here they're asking us to find the maximum tension. So basically the friction coefficient is still mu equals 1, and we have to talk about the maximum tension here. So let's take a differential element here. So I'm taking this particular element over here. So let's say the length of this part is r d theta. So I'm taking this angle as d theta. Okay, so let's draw an enlarged triangle. So this is r d theta. Now let's say, guys, if I take the angle with the vertical as theta, then r d theta will make the angle of theta with the horizontal, because r d theta represents the tangent, right? The tangential direction. So the tangent will make the angle theta with the horizontal, then the normal will make the angle theta with the vertical, right? So it's perfect. So now, guys, for a second, let's forget about the rope, and let's say we keep a mass somewhere on this cylinder. Okay, and the friction coefficient is the same as the last question, mu equals 1. So now if there is a question that will the mass slip or not, that will depend upon angle that the tangent makes with the horizontal, right? So if it is greater than the repose angle, if you guys don't remember, the angle of repose was the angle at which mg sine theta is balanced out by mu mg cos theta. Okay, so this is called the angle of repose. From here we get tan theta equals mu. And if we try to increase the angle theta by even a little bit, the block will start slipping. Okay, so this is called the angle of repose. So basically if I want to figure out if this mass will slip or not, all I have to do is check out what this angle theta is. If this angle theta is less than the angle of repose, then it won't slip. Otherwise it will slip. Okay, so in this case, if mu equal to 1, the repose angle is tan inverse of 1, which is 45 degrees. So if the angle is greater than 45, it will slip. Otherwise it won't slip. Okay, similarly, okay, so now if we go back to this situation over here, the limits of theta is minus 45 to plus 45. So if we just look at this positive region, it is always less than 45 degree, right? So basically theta is less than theta repose, which is actually 45 degrees, right? So basically, in this r d theta element, okay, so now let's bring back our rope, okay, and I'm going to place the rope on this incline. So this is a very tiny, so this is a tiny part of the rope, okay, whose length is r d theta. So now what are the forces on these? So firstly, we have the dmg sine theta down the incline. Then we have the friction force F. Then we have the friction force F. Then we have tensions, right? Now, but the key realization here is that as theta is less than the angle of repose, it will never slip in the first place. Okay. And if it never slips in the first place, it wouldn't be pulling on the other parts of the rope, which basically means that friction is less than its limiting value. So basically, friction by itself can balance out the dmg sine theta in this particular case. Okay. Also, in other words, means that the tensions won't even develop at the ends of the DL element. So the tensions at these 2 points are just zero. Okay. So this is similar to that question, similar to this particular question where you have two blocks that are kept on a floor and the friction coefficients are given. And then we have a time variable force, which is increasing with time. So firstly, what will happen is the friction F2 starts building up over here. And once it crosses its limiting value, then only the tension starts building up, right? So till the limiting value is reached, there is no tension in the string. This situation is also similar to that. So as friction is self-sufficient for balancing out DMG, so the situation is as good as just keeping it on a horizontal floor. Okay, so in this situation, obviously, the tension at each cross section would be just zero. So the answer to this question is that the tension is that whatever cross section you choose, the tension everywhere will just be zero. So another way to visualize this is that you can train connected by strings. Okay, something like this. Okay, so here what happens is if you keep a block, it won't slip, which means tension is zero. And you can say the same thing about each of these blocks. Okay, so yeah, that was it for this question. If you guys have any doubts, you can comment down below. And if you enjoyed the video, please do like, share, and subscribe. And that's it. Thanks for watching.